For some compounds, the molecular ion peak is not the base peak. Consider, for example, the mass spectrum of benzene, which is shown here. Clearly, the molecular ion, which would be at mass over charge of 78, right? Because benzene is C6H6. We have, for a carbon, we have an atomic mass of 12 times 6, which equals 72. For a hydrogen, we have an atomic mass of 1 times 6, which equals 6. We tally that up, we get 78. So our molecular ion is at 80, 79, 78, right here. Looks good. Now clearly you can see that the molecular ion is not very susceptible to fragmentation. There aren't very many fragments here. And so the molecular ion is the most abundant fragment to pass through the spectrometer. This is generally not the case. Most compounds will easily fragment, and the molecular ion peak will not be the most abundant ion. For example, take a look at the mass spectrum of pentane, which is shown here. In pentane, the molecular ion, which is right here at 72, so this is M over Z is equal to 72, you can see that the molecular ion is very small. And again, where does that molecular ion come from? Well, pentane is C5H12. And so from our carbon, we have 5 times 12, which equals 60. And from our hydrogen, we have 12 times 1, which is equal to 12. We tally that up and we get 72. And you can see that in the mass spectrum of pentane that the most abundant ion, the parent ion, is right here at a mass over charge of 40, 41, 42, 43. So this is 43. And since it's the most abundant ion, this is the base peak. And it is assigned a relative abundance of 100%. In some cases, it is possible for the molecular ion peak to be entirely absent if it is particularly susceptible to fragmentation. In such cases, there are more gentle methods of ionization other than electron impact ionization that allow the parent ion to survive long enough to pass through the spectrometer. Useful information can also be obtained by analyzing whether the molecular weight of the parent ion is odd or even. An odd molecular mass generally indicates an odd number of nitrogen atoms in the compound, while an even molecular weight indicates either the absence of nitrogen, so no nitrogen, or an even number of nitrogen atoms. This is called the nitrogen rule. So if we take a look at this molecule here, this is pentane. It has no nitrogens in it, and you can clearly see that it has an even molar mass. If you take a look at this compound here, it has 1 nitrogen in the compound, and therefore it has an odd molar mass. And you can see that rule here. A molecular ion with an odd mass generally means that there is an odd number of nitrogen atoms in the molecule. And so just by looking at the mass of the parent ion, we can say it's odd, so there's probably an odd number of nitrogens, and there's 1. And if you look at the last example here, you see that there are 2 nitrogen atoms, and so we go back to having an even mass. And so it's important to examine the molecular ion from the point of view of the nitrogen rule for every mass spectrum that you look at.